Good morning, everyone. So my name is Murtadha Aldeer. I'm a PhD student working with Professor Rich Martin. This is joint work with the collaboration of Professor Rich Howard and Professor Ortiz. We modified the title a little bit from the one in the agenda because we are in the process of submitting this work to one of the ACM conferences. So I will talk about our ongoing work on system for patient discrimination from in-bottle sensor data using off-the-shelf accelerometer sensors. So I'll start with a few facts. I think most of these are mentioned by other presenters this day. So as you are noticing that the people aged 60 years old or more are increasing these years. Some statistics shows that this number will multiply by 100% in 2030, but another paper says this number will be multiplied by 250 times in 2050 as compared to 2013. And thanks to the involvement of the technology in this field, one example is as I think Professor Ortiz mentioned, that if you are an elderly person living in a home alone, so your physician will maybe ask you to buy a specific device to monitor your motion, or just in case you need emergency, you press one button and then the ambulance will come to you or help or something like this. Another important thing is we do, for example, also to maintain this thing, we need to go to doctor at least every 1 year to do physical check. Another strategy is the correct medication, and I will focus on this. So once someone is evaluated as sick by the physician, so the first solution is the doctor will ask you to go to the pharmacy and pick a specific medication. But here's the problem. There is a lot of, hundreds of papers on this field. That's the field of medication adherence. So there are a number of problems. For example, either the patient doesn't fill the prescription, he doesn't take the medication at all, or he buys the medication but he doesn't take it and finish it. Sometimes it takes the patient takes the medication but doesn't take it on time. 3 times a day, he'll take it 2 times a day, and that's it. So this will cause a lot of problems, like going to the hospital a lot, and maybe in certain situations will lead to death. So there's a lot of work that has been done on medication adherence, and more specifically medication adherence monitoring. And since we are in the technology sector, we focus on the medication adherence monitoring systems based on technology solutions. So there is we reviewed this in the paper with Professor Jamal Mard and Professor Martin. So this is, and here I will list a few of these. The first one is using proximity sensing. So by proximity sensing, for example, here in this picture you see a drawer that has number of pill bottles, one here. So each of these pill bottles has RFID tag attached to it. And there is a reader, that's the green one here. So once the bottle is removed from the drawer, the system will detect that this bottle is not within the range of the reader anymore. So this will be counted as one medication taking. Now, the other one is the vision-based system. You see this picture where the patient should sit in a specific room facing the camera and make specific motion to show that he's taking the medication. So, but imagine, the patient cannot, in this case, if he is traveling or is visiting someone and taking medication, then this will not be counted as medication taking. So these systems are not accurate. Third one is using ingestible biosensors. So they use pill bottle or capsule, and inside this a pill or a capsule, and inside this capsule there is small RFID tag. That's as the size of sesame seed, and they ask the patient to swallow the pills, and but in order to detect that, I mean that the capsule has been swallowed by the patient should be wearing an RFID reader. It's like a band there. So imagine that he should be moving all the time, maybe, or wearing it 3 times a day, or whenever he's taking the medication in order to detect this. The fourth one is the wearable sensors, like using the smartwatch and the sensors inside this smartwatch. For example, the accelerometer to monitor the motion. That's the hand-to-mouth motion, or the motion when associated with picking up the bottle, for example, or using a neck wall sensor that monitor the vibration of the throat, for example, when swallowing something. But you see, I mean, this is not comfortable for the patient. The last one is using smart pill bottles or containers, and I'd like to focus on these. So the containers can be similar to these, similar to the medication cabinets that's available at homes. But these systems are bulky and it requires a lot of things, like a camera, maybe a load cell, a switch sensor in order to detect the opening and the closing of the container, and it can be confusing. Like for example, here there's a number of compartments, maybe 52 or something like this, and in each compartment there is specific medication, and the patient should go and take a medication from one of these. So this can be confusing. The smart pill bottles is similar to these simple pill bottles that are available from the pharmacy, but it can be equipped with sensors. So in this contest, we focus on pill bottles, but we'd like to make them more smart by embedding more sensors inside these bottles and collect more data from the user from only this smart bottle that's off the body, and allow maybe the mobility at least within the home environment, and can be battery powered. I mean, imagine in comparison with the wearable sensor, if there's an older person living alone at home, in the home, and you ask him to wear a smartwatch or a wearable sensor, but replace the battery every 2 days, for example, or recharge the smartwatch every two days. We think this will not work. Also, we think that the few important applications that can be enabled using the smart pill bottles. First one I already talked about, that's medication adherence monitoring, but we don't want to just monitor the medication adherence or compliance of the patient only. We would like to see who has if the patient has taken the medication, and if if the patient himself or another person. And the other application is also related to this. That's the drug abuse monitoring. So some papers show that the emergency visits of the children that's in the age of 5 years old or less, among those who are aged 18 or less, was the highest in the U.S. That's due to the drug poisoning. Like I have a friend of mine. She's doing also a PhD here in the civil engineering department. Like she has a daughter that's 2 years and a half. They have their grandmother visiting them. So she swallowed stolen 5 pills of the medication that used for hypertension from her grandmother and swallowed them. So she ended up in the emergency for one night, measuring her, the blood pressure every 2 hours. And this happened here, like 3 weeks ago. And so unfortunately that's the result of the busy life that we have, or unsupervised medication overdoses, and the easy access to the medication cabinets available at home. So we are really in need for a real-time monitoring system to detect such activities, who has taken the medication and when, and maybe issuing some warning system, some warning messages. But how can we use this simple smart pill bottle to differentiate different users? So we have done some experiments. In fact, we got the IRB approval from our school. So here I give example from 3 users. We built a simple pill bottle as shown here. That's the yellow one, and we asked number of users to take medication. In fact, there is no medication here. There is a candy pills or sugar pills, you can call them. And we asked them to take the 10 candies from the bottle the normal way that they will usually do. So here you'll see that the first user picked up the bottle and flipped it clockwise. Second one was sitting, and he took the medication, but he flipped the bottle anti-clockwise, I think. Yeah. The third one, that's most interesting one, is he picked the bottle, and he was taking the medication like this. So he didn't flip the bottle at all. And furthermore, he didn't, if you notice, he didn't put the cap on the table. He kept the cap like this. So each one of the users has his own way on taking the medication. And we think this can be similar like to the way of walking, like each one can be identified from the way that he walks, right? So we think that we can identify the user that's taking medication from the way that he is taking the medication. In this context, we propose patient sense system. Here we show the architecture that we use for collecting the data from the users. This is our simple prototype. You see it has this funny and simple shape because I'm not a professional in 3D printing, unfortunately. So we started with this model of per bottle with this prototype, and we embedded 2 accelerometers, one inside the cap and one in the body. That's here below the compartment. And we used PipTag. PipTag is low power wireless sensor node developed at WINLAB like 10 years ago. That's this one. So PipTag can be its low power one and can be powered from a coin cell battery. And also we use a switch sensor. That's magnetic switch sensor. That's just to detect the opening and the closing of the cap. The pipeline that we used in patient sense is shown in this slide. So we start by collecting the data from number of users. We do some data pre-processing steps. That's removing the gravity, this contribution of the Earth, because we are using the accelerometers, and extracting specific segments that we are interested in from the raw data. Then we put all these segments, we call them later pulses, in a bag of pulses. We call it a bag of pulses, and we'll show you these later. Then we extract some useful feature based on this time series data that we collected from the accelerometer, and feed these features in the matrix to several classification techniques in order to classify the patient and identify the patient. So here is an example of the raw data that we collected from one of the users from the accelerometer. We have the XYZ axis, but we are only interested in the pulses or these segments that correspond to medication taking. So this is like when the bottle is picked like this and maybe shaked a little bit in order to get one of the pulls out. So we do some simple thresholding. We apply some simple thresholding techniques in order to extract these pulses and put them in a bag like this. I mean, we put all the extracted pulses from all the users from all axes in a bag, and then we measure the distance between each pulse and all other pulses. Like it's like pairwise distance, measuring pairwise distance between all the pulses. We use a technique called DTW, that's dynamic time warping. So this is one of the efficient techniques that can be applied to time series data to measure the distance between two signals. And the output from this will be a distance matrix, as shown here. That will give us the distance between all among all the pulses that we have from all the users from all the axes. But the distance between two pulses from the same user will be short in this case. Why we use the DTW? So here's an example of the point-to-point measuring of technique used for the measuring the point-to-point distance between the signals that are similar to each other using the Euclidean distance. And here is the DTW. So DTW allows some elasticity. In fact, take this an example. If someone is attaching an accelerometer to his body and walking, if I walk for 10 meters, I can finish this within 10 seconds, for example. But if I walk faster, I can finish it within 7 seconds. But at the same time, I am walking the same way. I'm the same person. So the signal would be the same, but maybe of different length. With DTW, there is a math model behind this that allows doing this. DTW will allow like different will help in computing the differences between the points that are better aligned. Like take, for example, take this point and this point. With the point-to-point distance, this is not possible. In fact, the other technique will give us a distance between the two, but no, it will not be as accurate as the second one. So once we have the distance matrix from that we obtained from all the pulses, and in order to get a useful set of features based on these pulses that we extracted from the raw data, we apply a clustering technique, which was very well known, called the k-means. Here, the number, I should mention this, like the number of clusters, if I have X users, so the best number of clusters should be X in order to put the pulses that I obtained from each of the users in one of the clusters. But no, this is not the point. So in each case, we pick a number of clusters, and we evaluate it using evaluation measure called the silhouette score. So the highest is the better. And we feed the distance matrix to the clustering technique in order to put these pulses in that number of clusters. So in fact, we are labeling these pulses in this case. For example, here, the clustering technique told me that this small pulse belongs to cluster 3. This pulse is the big one belongs to cluster 5, and so on. So at the end, we'll end up with a pattern. For example, user 1 will have a lot of 5s, for example, on the x-axis, and then a lot of maybe 4s or 1s in the y-axis. A lot of 5s and 3s in the x-axis, on the z-axis, sorry. Here I show the raw data from the sensor that's on the body of the bottle, and the raw data from the sensor that's embedded in the cap of the bottle. So after obtaining the distance matrix between these using DTW and feeding it to the clustering technique, we get the labels of these pulses. The way that we construct our feature vector is this, like the feature vector that I will feed to the classification technique will be these labels like 353, 430, because we allow up to 3 words for each medication technique, for each medication taking operation. In this case, I mean, we'll capture the small pulses as well. The same thing for the data that we obtained from the cap. And then we join them, so our feature vector will be like this. So this corresponds to one medication taking operation. And we will use these feature vectors in order to build our in order to build our feature matrix and feed it to the classification technique. The classification approach that we consider in this work is two approaches. The first one is two-class approach. That's when we are trying to identify if this is the patient or any other person. For example, if I have a family of 5, I'm interested on only detecting if the medication has been taken by the patient himself or not. So I have like two classes in this case, either 0 or 1. So 1 will be the patient, 0 everybody else. But I don't care who's else. For this, we use the binary SVM because it's a binary support vector machine, because it's simple, lightweight in computations, and we'll see later it performs well. The other approach we used is the multi-class approach. So that's in the situation when where we are trying to identify a specific person in the set. Like, for example, if we have a family of 5 again or 4, but we'd like to find out who has the exact person that has been taken, use the bottle and taken the medication. So we used two approaches in order to compare them. That's the multi-class SVM and the random forest. And in order to evaluate our approach, we played with a number of things, like number of users in the data sets, the training set size, the classification algorithms, and the number of sensors. That's are we able to get a reasonable accuracy of classification from one sensor only? Because here I said we are using 2 accelerometers, but can we achieve a reasonable accuracy using 1 accelerometer only? In this case, we'll reduce the cost and the energy consumption, because in each of these, I mean, we'll need to replace the battery maybe from time to time. So we conducted a number of experiments using 16 healthy adults, 14 males and 2 females. The ages of them were like from 18 to 64. Each participant were asked, each of them were asked to take the 10 candy pills out of the pill bottle without consuming it, of course. And we think that our approach is will promote like low power, because we use low sampling rate, like 10 hertz only, 10 times a second. In comparison to other studies, they use 50 or 30 at least. We used also the camera for ground truth, and I show you some examples from the experiments. Here, this is the result of varying the number of users. So here, this is the number of users, and since this is binary SVM, this is only 2-class SVM. In this case, we are trying to discriminate, for example, 1 out of 2, or 1 out of 4, or 1 out of 8, and so on. So overall, the accuracy was over 90% in this case. I think the title of this slide is wrong. This is the effect of changing the training set size. So we started with the 50% up to 90%. So imagine it like this: if we have 50% of the data for training, this corresponds to 5 times of medication taken. 90% means it corresponds to 9 times of medication taken, because that's the number of times that we train our system on. And overall, the accuracy was over 90% with the different training sizes. Here I show the results of the for multi-class classification, where we are trying to find the or identify the exact person who has taken used the bottle and taken medication. So we see that random forest used achieved higher accuracy in comparison to multi-class SVM with and here I take subsets and focus on this number. That's three people because these days the number of people in the family in the US is less than 3 people. In fact, if you go to this and check to this link and check, you'll see that the number of people is less than 3 members in the family. So if we are trying to discriminate one who has taken the medication in a subset of 3, we can achieve this with accuracy that's higher than 91% using the random forest. Lastly, here's the results that we obtained for one sensor. This is for the using the sensor that inside the bottle only, and the dextrometer inside the bottle, and this is the data from the cap sensor only. So we can see that the binary SVM can achieve still achieve high accuracy with more than 93% when discriminating 1 out of 16. Random forest perform better as well in comparison to SVM with the 82% of accuracy when we are trying to classify, identifying one user, the exact user in a set of 3. So in conclusion, we believe that our system is accurate, performs well with the simple and low computation classification technique, that's binary SVM, and it is non-invasive and because it's off body, and slow power one because we use peptide, which is a low power system that can be powered from a coin cell battery. More than this, we use low sampling rate, that's 10 hertz only. And we think this system will enable a number of important applications. Thank you very much for listening to my talk, and I'm happy to answer any question.